already sassy. Our session will be starting soon. This session will be recorded so that you may come back to it later if you need, and so others who may have missed out on today's events will be able to come and watch it. So now, at this time, please mute your mics for the best sound experience, otherwise the feedback could interfere with information we will be sharing. We'll be sending the 1324 room link on the chat so that you may connect to your session if you're here for Math 1324. Ms. Patricia will be sending individual messages to everyone to gather your student ID numbers to sign you in. Without further ado, I'll pass it on to our presenter so that we may begin.
Well, good morning, everyone, and thank you again for joining us this Friday for the Friday Happy Math Hour. I don't know how you all feel, but this is our last Happy Math Hour for the semester, for the year. We will be doing the final review. Hopefully, all of you are doing well in your classes, and I know you'll do great on the final as well. So, without further ado, let's go ahead and get started on our review. Um, so we are going to touch on a few topics, and so let's start with this one. Find any intercepts and test for symmetry with respect to both axis and the origin. And we have this equation, y is equal to minus 2x plus 1. So the first thing we want to do is let's do the intercepts. So to find the x-intercepts, we set our y equal to 0 and solve for x. Yes, so 0 is equal to minus 2x plus 1. Subtract 1 on both sides, divide by a negative 2, and we find that our x-intercept is 1/2. Okay? To find our, and this is the point, right? We have our ordered pair. We start, the x comes first, it's the 1/2, and our y was 0. Okay, to find the y-intercept, we set x equal to 0. So we have y equals minus 2 times 0 plus 1. So minus 2 times 0, or negative 2 times 0 is 0. 0 plus 1 is 1. So our point, our ordered pair, is 0, 1 for the y-intercept, or an equation format, y equals 1. Now, so if we were to graph it, okay, we would have our graph this way, right? We have it crosses the x-axis. Excuse me. We're checking for symmetry. So to check for symmetry, let's look at x-axis symmetry. So for x-axis symmetry, what we do is that if we change the sign for y and we still have the same equation, then it has that respected symmetry. So let's go ahead and test if it has x-axis symmetry. So we have our equation y equals minus 2x plus 1, and we're going to replace the y with a negative y. Okay. So when we do that, we have negative y is equal to minus 2x plus 1, and if we would solve for y again, we end up with a new equation, y equals 2x minus 1, which is not the one that was given. In the one that's given, we have a negative 2 for the slope, and in our new equation, we have a positive 2. So this equation does not have x-axis symmetry. So let's go ahead and check for y-axis symmetry. We do something similar. Now we change the sign of the x. So we go ahead and do that, replace x with a negative x. And if you see, we end up with almost the same scenario as well. We have y equals to 2x plus 1. This also does not have y-axis symmetry. And then to check for origin symmetry, if we change the sign of the x and the y and we have still the same equation, then it would have origin symmetry. So let's go ahead and test for origin symmetry. Let's go ahead and replace the x and the y with a negative symbol. And when we solve for y, we have y is equal to minus 2x minus 1. Even though we come close, these two equations are not identical. The original equation has a y-intercept at 1, and this new equation has a y-intercept at negative 1, right? So our c value changed. So hence, this equation does not have either x, y, or origin symmetry. Let's look at another example. write the standard form of the equation of the circle with the given characteristics. We have the circle is the center at -4, 2, and we have a radius of 2. So to write the standard form of a circle, we need to know the format. So the format for the standard form of a circle is given by this: x minus h squared plus y minus k squared is equal to r squared, where h and k is our center and r refers to our radius. So in this particular problem, we're just plugging in, right? So let's go ahead and plug in what we know. We know the h, we know the k, so we have x minus a minus 4 squared plus y minus 2 squared equals to 2 squared. Let's go ahead and simplify. Um, so when we simplify, we have a negative with a negative is a positive, so that gives us x plus 4 squared. There's nothing to simplify here, and 2 squared is 4, and voila, we have our equation in standard form with the center and given radius. Okay. Um, I do want to mention something. If I am going too fast, please let me know. Stop me, ask me questions, raise your hand, and I will slow down or stop or go back if need be. Okay, so let me know. So this next example is write equations of the lines through the given point parallel and perpendicular to the given line. Okay, so what we know is for us to determine whether two lines are parallel or perpendicular, that's determined by its slope. If two lines have the same slope, then that means that the lines are going to be parallel. If two lines have different slopes, well, we know that they're going to intersect. But for it to intersect at the particular point, for it to be perpendicular, it has to be a special slope, right? And I like to say it's the opposite slope of the parallel. So let's go ahead and do this one. Um, so it's telling us that we have to find the parallel and perpendicular lines to this given equation. And what I would do first, my first step is to convert this equation into slope-intercept form so I can see what the slope is. Because right now it's in general form and it's hard for me to tell what the slope of this line is. But if I convert it to slope-intercept form, I'll be able to see very easy what that is. So let's go ahead and do that. So I'll take 8x minus 2y equals 3 and convert it into slope-intercept form, which gives me y equals negative 3 halves plus 4x. And by me doing this, I can identify that the slope is 4, right? And so we give the variable m for slope. So if I want to find the parallel line um, to this given equation, its slope has to be 4, but then they give me that extra piece of information that it has to also go through this point, 8, 1. So there's several ways of doing this. The way I like to do it, I like to use what's called the point slope formula. That if I'm given a point and the slope, I can just plug in um, the the variables here to the unknowns, right? So let's go ahead and substitute. So we have here um, the x1 and y1 is a point that you want to go through, and again, m is a slope. So once I do that, I have y minus 1 is equal to 4x minus 8. Um, go ahead and simplify and distribute my 4. So 4 times x is 4x, 4 times a negative 8 is a negative 32. Add 1 on both sides and I get y equals to 4x minus 31. So this equation, if you see, has the same slope as the given equation, which has a slope of 4, has a different y-intercept. So this is the answer for the parallel equation. Now we need to define for the perpendicular. So if my parallel is a positive slope, well, opposite to that is going to be a negative slope, right? And also what I can do is I can convert this slope of 4 into a fraction, making it 4 over 1, and the reciprocal of this fraction, or the opposite of this fraction, would be 1 over 4. So that is my perpendicular slope. Um, so my perpendicular slope is given by the negative reciprocal of the given slope. So it's the perpendicular slope is negative 1 over 4. And again, I'll use my point slope formula to go ahead and find that equation. And I like this equation again because it's just plugging in. I plug in what I know. They're giving the point. I'm putting in the new slope, and I just have to distribute the negative 1/4, and this is going to give me negative 1/4 x plus 2, and then subtract 1 on both sides. Excuse me, add 1 on both sides, and that's going to give me negative 1/4 x plus 3. So this equation is the perpendicular equation to the given line because it has its opposite slope. Um, so, questions. All right, let's go ahead and move forward. Let's look at another set of examples. This particular one says find the following. We're giving the function f of x, which is 9x plus 1. We're given g of x, which is equal to x squared minus 4. And we have to do some basic operation with functions. The first one is adding function f with function g. So the way I like to write this is in this format. This is the syntax that the book gives us to do adding functions, but I like to separate them, just what they're saying. What they want me to do is add function f with function g. So all I have to do is substitute. Function f is 9x plus 1 plus function g is x squared minus 4. Then all I have to do now is just combine my like terms. So I only have one term that has a square or a square exponent, so that stays the same, but I have two, I also have one term that only has an x, that's not 9x, but I have two like terms. I have two constants. I have the plus 1 and the minus 4. So I can combine those. So plus 1 minus 4 will give me a minus 3. So that is the addition of function f with function g. B is very similar, except now we're doing a subtraction. So again, I like to rewrite it as f of x minus g of x. That way I just substitute. F of x is 9x plus 1 minus x squared minus 4, which is g of x. So the first thing I need to do to get rid of my parentheses is distribute that negative symbol or that subtraction. A negative times an x squared is a negative x squared. A negative times a negative is a positive 4. Okay, and then I do the same thing. I combine my like terms. Again, I only had one x squared term that stays the same. The 9x is nothing to combine, but I have two like terms. I have a plus 1 plus 4. Plus 1 plus 4 will give me the plus 5. So function f minus g is minus x squared plus 9x plus 5. So let's look at C. C is a product of two functions, a multiplying function f with function g. So again, very similarly, I like to rewrite them. I like to rewrite it as f of x times g of x. And I just now substitute. F of x is 9x plus 1. G of x is x squared minus 4. So to go ahead and simplify, I have to do FOIL, right? I'm going to distribute the 9x to x squared and to the negative 4, which gives me 9x cubed minus 36x. Distribute the 1. 1 times x squared is x squared. 1 times a minus 4 is a minus 4. And is there like terms that we can add? No, they're all different terms, so that is our answer. So again, we can leave this on the computer just the way we did the FOIL, or we can rewrite it, which I like to do that. It's in standard form, but you don't have to, where the leading coefficient and term has the highest exponent, right? So we have 9x cubed plus x squared minus 36 minus 4. All right, so let's do D. This is saying f divided by g of x, right? So I like to rewrite one as well. This is just dividing function f with function g. And then all I have to do is substitute. F of x is 9x plus 1. G of x is x squared minus 4. Now, if I were to able to factor anything out or simplify these two functions, I would do so to simplify my fraction, but there's nothing for me to simplify, so that's the answer for f divided by g of x. It's just 9x plus 4 over x squared minus 4. Okay. Now, you were also asked on the homework, that your instructor might test you on this, is to find the domain of the division of function f with function g. And we know that when we're looking at rational functions or fraction problems, right, we never want 0 on the denominator. So we need to ask ourselves, will x squared minus 4 ever result in a value of 0? So if we don't see it, we can set it equal to 0. We can say x squared minus 4 is equal to 0 and solve for x. And when we do that, we notice that x can be equal to plus or minus 2. So there is a value, this plus or minus 2 will give me 0 in the denominator. So hence, those are my restrictions on this function. So that is my domain. My domain in interval notation is from negative infinity to negative 2, union from negative 2 to 2, union from 2 to infinity. Okay? All right. Let's go ahead and look at another example. The problem says, does the function have an inverse? So let me do a little extra review as far as what this problem is asking. So we know that a function is a function if when if we have a graph and we do the a vertical line test, and if that's imaginary vertical line crosses a graph only once, then it's a function. But now it's asking us if this has an inverse function. So inverse again means opposite, right? So if a vertical line gave me um, the answer if the function was a function, well, opposite to a vertical line is a horizontal, right? So a horizontal line, if I do an imaginary horizontal line test for this graph, this will tell me if this graph has an inverse or. So if we do this, again, we can see that if we have this imaginary horizontal line, our horizontal line will only cross the graph once. So hence, this function has an inverse. Okay, so let's go ahead and see if we can have some more examples of this. So this problem says determine whether the function has an inverse function. So we have f of x is equal to the square root of x minus 8, where x has to be greater than or equal to 8. Okay, and if it does have a function or an inverse, let's find that inverse. So the first thing what we need to do is this is a square root function, and then we'll pass our vertical and horizontal line test, right? If we remember our parent functions, our graph has it's like a little on its side parabola, right? So let's go ahead and find its inverse. So the first thing that I do to find the inverse is convert this function into an equation, right? And that's replacing the f of x back with y. So we have y is equal to the square root of x minus a. Now I'm going to interchange or swap my x and y values, right? So my y values will become x and my x values will become y. So then this gives me x equals the square root of y minus 8. And what I'm going to do now is solve for y. So the first thing that I need to do to get rid of my square root is take the square of both sides. And when I do that, this is going to give me x squared is equal to y minus 8. Now I just have to add 8 on both sides. It's going to give me x squared plus 8 equals y. So this is just the equation. Don't forget on the test, if you're doing paper exams, um, to indicate that this is an inverse, our syntax for this is the function, but the exponent now is to a negative 1. Okay, this indicates that I am dealing with the inverse function. So it's the inverse of x squared plus 8. Okay, all right. Let's look at another example. The problem says, sketch the graph of the function by applying the leading coefficient test, finding the real zeros of the polynomial, plotting sufficient points, and drawing a continuous curve through the points. So we have a function g of x is equal to negative x squared plus 12x minus 32. And A says apply the leading coefficient test. So if we remember the leading coefficient test, um, And there were several cases, right? Um, so on this here, my leading coefficient is a negative one, right? So this is going to tell me that my graph um, is decreasing depending on the degree also of the function. So that's another thing that I need to know. What is the degree of this function? Well, the degree of this function is a degree 2. 2 is an even number, so hence this function is an even function. So by applying the leading coefficient test, says that um, if my leading coefficient was a positive number and it's an even, that means it's going to rise on the left and rise on the right. But if it's a negative number and it's an even function, it's going to fall on the left and fall on the right. So if we look at the examples or the options that we have for this problem, um, which one would it be? Well, it's going to be, well, and actually, I, I have what I just explained to you, the graphs here, as far as the leading coefficient test. So our graph is going to fall on the right and fall on the left, right? So, oops, don't mean to go too fast. Again, so on this one, let's see, rises, falls, left, and the left. So if you see, our answer would be if these were labeled as A, B, and C, it's RC, I believe, right? Okay, so again, be familiar with your leading coefficient test. You need to know the degree of the polynomials, and you need to know the leading coefficient, the sign. The sign will determine um, if it's pointing up or down on the directions. Okay. All right, let's look at this example, or still continue with the same example, minus x squared plus 12x minus 32. Let's find the real zeros of the polynomial. Okay, so um, on this one, because it's a quadratic, there's several ways to finding the zeros. We can factor it, use a quadratic equation, right? So for purposes, as we can practice factoring, okay, I'm gonna factor this guy out. The minus x squared plus 12x minus 32. So when I factor this, I get x minus 8 times x minus 4. So for these two products to equal to 0, either x minus 8 is equal to 0 or x minus 4 is equal to 0. So now it's easy for me to solve for x. So on the first one, x equals 8, x equals 4. Okay, so these are my zeros. These are my zeros for this polynomial, and I also know the end behavior based on my leading coefficient test. Now I'd like to find its intercepts. Again, to find the y-intercept, set x equal to 0. So my y-intercept here is negative 32. Um, Also using my formula to find the vertex, okay? Um, I discover that the x value of my vertex, again, using um, minus b over 2a, when this function is given to me in general form, where it's ax squared plus bx plus c. Here, a is negative 1, b is 12, c is negative 32. So when I apply these values here, I get x is equal to 6. So that's the uh, x value of the vertex. To find the y value of the vertex, I just plug in this value 6 back into the equation. So when I do that, I have minus 6 squared plus 12 times 6 minus 32, which gives me 4. So the vertex of this parabola is 6, 4. All right, so now we are able to, with all these points, try to connect the dots and have a smooth curve, right? And hopefully at this point in time, we know that we were dealing with a parabola, so we can smooth out that curve for that parabola, okay? All right, so let's review another concept. Let's review the find or the zeros of a polynomial by practicing our rational zero test. And the rational zero test is the way to find possible zeros, right? It's a test, right? Like when we were taking tests for COVID, right? It's either positive or negative. We want it to be negative, not positive. But Yeah, this is just a test. It could give us the true zeros or not, right? So the way we use the rational zero test to find the possible zeros of a polynomial um, is we grab the constant term and we find its factors, and we divide that by the leading coefficient factors. So as an example, this function x cubed plus x squared minus 9x minus 9, my constant is a 9. Now, I'm only interested in the value because um, by using the test, I'm going to look at all possibilities, the plus or the minus factors of it. So it doesn't matter that it was a negative or a positive. I'm just interested in the value. So 9. So the factors of 9 are 1 and 3 and 9. So I'm going to be testing the plus 1, plus 3, plus or minus 1, plus or minus 3, plus or minus 9. I'm going to divide that by its leading coefficient. On this particular problem, my leading coefficient is a value of 1. So that's just plus or minus 1. So when I divide these values, I get these. These are the possible zeros. -9, -3, -1, +1, +3, +9. Okay? So this is a way to find possible zeros using the rational zero test. Now, if I want to determine if any of these is a true zero, let's practice using synthetic division. So let's use synthetic division. Again, synthetic division will apply only the coefficients of the term. So here we have 1, 1, -9, -9. And again, I'm testing the first value, x equals 1. Is 1 a zero of this polynomial? So let's go ahead and do the synthetic division. I bring down my 1. 1 times 1 is 1. 1 plus 1 is 2. Multiply 1 times 2. That gives me 2. So -9 plus 2 is a -7. 1 times a -7 is a -7, and -7 plus -9 minus 7 is a -16. This is the last value is always our remainder. And since this our remainder is not 0, then this 1 is not, right? This Chuka is sad that we didn't get a 0 because 1 is not a 0 of this polynomial. So let's go ahead and try another one. Um, let's go ahead and try -1. Again, we'll go through our process. And when we do this, oh, awesome, right? -1, our remainder ended up to be 0. So x equals -1 is a 0 of this polynomial. Now, will this help us? Because our quotient here, now that we know one of the zeros, our quotient, if we write it back as an equation, gives us x squared minus 9. And also always keep in mind that when you're dividing, you're going to lose a degree of your polynomial. You factored it down a degree. Okay, so the first term here is going to be a square. There is no x term, and this -9 is a constant. Now, for us now, it would be very easy to find the remaining zeros. Like when I look at this polynomial, degree 3, it possibly can have 3 turning points where it's going to cross the axis at three places. So I should have 3 zeros. So if I solve for the x on this one by using my square root property, I'm going to add 9 on both sides, take the square root on both sides, and this is going to give me the square root of 9, which will be plus or minus 3. And there we go. This polynomial has 3 zeros. Our zeros are x equals -1, x equals -3, x equals 3. Now let's go ahead and graph the polynomial. So again, we're going to graph it on xy axis or on our rectangular coordinate system. Let's plug in what we know. We know that these are the points where it crosses our axis at -3, -1, and +3. But we don't know the behavior or what's going on between these dots, right? We do know the end behavior because of our leading coefficient test. Again, this is a polynomial of degree 3, which is an odd function. its leading coefficient is positive, so then I know that my graph is going to fall on the left, rise on the right. But I don't know what's happening in here. So for me to find out what's happening, we like to pick a few points between um, these x-intercepts to see what the graph is doing. And again, for our purposes, I picked -2, +2, and 1. And when I plug in these points, okay, it allows me to get this somewhat smooth curve. Yes. So this is a way for you to graph polynomials. And one way to make our life easiest is to simplify it. And with that, we can use synthetic division or division, okay, to make those polynomials a lot nicer to use functions that we know. All right, let's look at this example. Um, oh, let's skip this question, and then if we have time, we'll come back to it. Okay. All right. How about this one? Um, let's practice this rational function, right? We have f of x is equal to 1 over x plus 3. And the first part A says state the domain of the function. So we practiced a little bit already this, right? That we know that when we have a fraction, we never want this denominator to be equal to 0. So we said x plus 3 equals to 0 in case we can't see it. Solve for x, and we notice that x equals -3. If x equals -3, -3 plus 3 will give me a 0. So what would be the answer for this? It would be all the values excluding the -3, right? Which is the last one. All right. Let's go ahead and identify all the intercepts. Let's start with the x-intercept. Again, we've done this already. Set y equal to 0 and solve. So on here, we have 0 is equal to 1 over x plus 3. We're going to multiply both sides by x plus 3. And when we do this, it's going to give us 0 is equal to 1, which is a false statement. So because this is a false statement, what this is telling us that this function does not have any x-intercepts. So again, what you would enter or you would write on your paper is for the x-intercepts, they don't exist. There aren't any. Okay. Now, to find the y-intercept, we set x equal to 0. And on that one, we do have, right, an x-intercept. We have, sorry, our y-intercept is 1/3, right? All right, let's do C. Find any vertical and horizontal asymptotes. Um, so first of all, the vertical asymptotes. That one's the easy one, or I like to say it's the easy one because any vertical asymptotes are any restrictions on our domain. So, and we've already done that. We found the restriction on the domain, so hence that restriction is a vertical asymptote. It's a value that my graph cannot cross or touch. So again, a vertical asymptote is a vertical line. We represent it as a dashed line. I know it looks like dots here, but it's a dashed line. And it's an imaginary line that our graph will not cross or touch. Okay. So on our given problem, when we solve for the restriction on the domain, what we actually solved for as well was the equation of the vertical asymptote. This x equals -3 is our restrictions, hence it's our vertical asymptote. Now and it's represented again as a dashed line here at -3. Now for our horizontal asymptotes, that's a little different story. We have several cases that will determine if we have a horizontal asymptote. So the first case is if the degree of the numerator is smaller than the degree of the denominator, then we will always have a horizontal asymptote at y equals 0. If the degree of the numerator is equal to the degree of the denominator, then we will have a horizontal asymptote by the ratio of the leading coefficient of the numerator divided by the leading coefficient of the denominator. And then we have the last case that if the degree of the numerator is greater than the degree of the denominator, then there exists no horizontal asymptote. But again, this will lead to um, possibly having a slant asymptote. Okay, so these are our cases. Again, horizontal asymptotes are horizontal lines, imaginary lines that our graph cannot cross or touch. So if we go to our example, we can write our numerator as x to the 0. X to the 0 exponent, anything to the 0 is 1. So if I look at my numerator, would have a degree of 0. My denominator has a degree of 1. So hence, on this one, the degree of the numerator is smaller than the degree of the denominator. So this has a horizontal asymptote at y equals 0. Okay, so this is my horizontal line in blue. Now, if I wanted to also graph this, okay, we have this information. We know that it doesn't cross the x-axis. It has a y-intercept, the vertical asymptote, horizontal asymptote. So if we want to graph this, we would need some additional points as well, okay? So let's go ahead and plug in what we know. We know the y-intercept here at 1/3. Additional points, I'm just picking -2 and 2 here to give me a better sense of what I'm looking at. These are my points. Okay. Um, if we know our parent functions, we would see that these are kind of like these parabolas, right? That are coming close to our asymptotes but never cross or touch. Okay. And we're cheating here. We're using the computer for it to draw it, not by hand, because it becomes all squiggly lines. All right. And as an example, this is what we would have maybe in our calculator. Um, our web-assigned homework gives us a multiple choice. Hopefully, it's very easy to see which is our answer for these, right? So you can see that it's that first option that is our answer. Okay. All right. Oh, let's look at this one. Use properties of logarithms to expand the expression. I like this one a lot. So we have a log here that has the same base. And we have a first thing, we have a division going on. So what I can apply is my quotient rule to expand this log. And my quotient says that when I have two things being divided, it's also the same thing as subtracting both of the logs. So this expands to the log of base 5 of the square root of x squared minus 9 minus the log of 5 to the fourth. Log to the fourth. Log of base 5 to the fourth. So what I see now is I do I have any exponents? And the answer would be yes. The square root can be written as an exponent. The square root is represented by a half. And by me doing this, I can now apply my power rule that if I have an exponent, I multiply that exponent to the log. So this is going to give me 1/2 log of base 5 of x squared minus 9 minus the log of base 5 of 4. Um, and we're not done. You might think we're done, but that x squared minus 9 can be rewritten. I see that's a difference of squares, which is a product. Okay, so x squared minus 9 can be rewritten as x minus 3 times x plus 3. And by me doing this, this becomes a log where I can use my property, which is the product rule. And the product rule says that when I have I have a log of the same base and inside the log I have items that are being multiplied, they can expand by addition. So I have 1/2 log of base 5 of x minus 3 plus 1/2 log of base 5 of x plus 3 minus log of base 5 of 4. So expansion means taking an expression of one single log and converting it to multiple logs. In this particular one, I was able to get 3 logs out of 1. Okay. All right. Let's move forward. Um, let's skip these as well, just so we can get to see other examples. Um, or we'll do the natural log since the one that I did was a science log. Let's do a natural log, the ln, excuse me. So So let's do this one, the natural log. So it says solve the logarithm algebraically. Oh, this one's our solving. Let me see, did I went too fast? Um, oh, condensing here. Oops, I don't have the answer for my condensing. Oh, but here. Um, yeah, let's do it. I want to do a condensing. Let's condense. We'll just condense the ones that I have. It's that way I don't have to erase it. So let's condense. We're condensing A. So we have log of x minus 6 log y plus 7 log z. So the first thing that I want to point out that these are all the same logs, even though they didn't write the base. When they don't write the base, we automatically assume that these are logs of base 10. Okay, so these are all equal, so I can condense them. So let's go through it. I just like to go from left to right. That's the way I read. If there's no parentheses, no special operations to do order of operations, I just go from left to right. So I have two logs that have the same base and are being subtracted with each other. So to condense them, I am going to divide the input. So I have log a base 10 of x divided by, oh, sorry, I skipped a step. See, I want to get through this. Um, Before I start condensing, everyone, I have to follow order of operations and see if I have any exponents, anything that's being multiplied to the log. So if I see here on the second one, I have a 6 times the log of y. That 6 is an exponent. That 7 times the log of z, that 7 is an exponent. So let's do that first. Let's do our power rule. So we have log of x minus log of y to the 6 plus log of z to the power 7. Okay. Now that I don't have anything being multiplied to my logs, I don't have any exponents, now I can start applying my condensing rules. So again, I have two logs that are being subtracted from each other. So we have the log of base 10 of x divided by y to the 6 plus log of z to the 7th power. Now I have two logs of the same base that are being added with each other. That's the power rule. So I just multiply x over y over 6 times z to the 7, which gives me um, log of base 10 of x times z to the 7 divided by y to the 6. Okay, so that's condensing. Let's go ahead and solve logs. And to solve, what we're going to do is we're going to have to condense sometimes. So a perfect example is this first one, and we have a natural log to work with. So that's great. So let's do A first. So the first thing that I want to do before I want to solve for x, is I'm going to apply my quotient property because I have two logs that have the same base. They're both natural logs, and they're being subtracted, so I can divide their inputs. So this is the same thing as a natural log of x divided by x plus 6 equals 7. Now, one of the things that I can do, I can do this problem several ways. I can use the inverse properties, or what I can do is change it to exponential form. And that for me works great. So what this is telling me is if I have the log of x over x plus 6, again, so you can see it better, let me convert it to the science log. Log of base e of x over x plus 6 is equal to 7. So again, my base is e of the log, so that's going to be the base of my exponential, which is e. The output of the log becomes the input of the exponential because logs and exponents are opposites of each other, inverses of each other. So they work backwards, right? So the input of the log becomes the output of the exponential. So we have e to the 7 is equal to x over x plus 6. Okay, so what we can do is we can multiply x plus 6 on both sides, distribute the e to the 7, okay, and factor out the, um, or move everything that does not have an x to the right and everything that has an x on the right to the left. So we can condense them. So we have e to the 7x plus um, e to the 7th. So again, I keep getting ahead of myself. So let's go ahead and again do what I just said. Move everything that has an x to the left, anything that does not have an x to the right. By me doing this will allow me to factor out an x so I can isolate it. So we can have x equals e to the 7 minus 1 is equal to negative e to the 7 times 6. And again, I'm doing all these values. I don't want to use a calculator yet. I'll use my calculator at the end, okay? So I'm going to divide both sides by e to the 7 minus 1. And this is going to give me x is equal to negative e to the 7 times 6 divided by e to the 7 minus 1. Now I can just go ahead and plug that into my calculator. Um, and again, I have a little snapshot of the TI answer. Our problem set to round our answer to 3 decimal places, so our answer would be negative 6.005. Okay, all right. Let's see. We've got 10 minutes. Let's see if we can. Oh, before I don't want to go too fast on this one. It's very, very important that you check your solutions. Okay, when you get an answer, make sure you plug that back in into the problem to see if it's possible. And here, if we check our solution, since we have the natural log of a negative value, this is going to give us an error. So on this one, this has no solution. Okay, so it's crucial, very important that yes, we did all this work, but we want to always check that our answer does satisfy our problem. Check, check, check. Remember, you guys will have plenty of time on your finals. Let's see. Let's go ahead and see if we can do something different. Let's skip through some of these. I want to get to see different topics to help you guys get ready. Oh, let's do this one. Solve the logarithmic equation algebraically, approximate to 3 decimal places. So we have the log of base 9 of x minus the log of 9 of x minus 8 equals to the 1/2. So to solve for x, the first thing that we'll do is we want to condense that left side. And we're going to condense it using our quotient property because I have two logs that are being subtracted by each other. So this is going to give me the log of base 9 of x over x minus 8. And yes, again, remember you can always download this presentation so you can look at it slower and also review all those the ones that I skipped. You're able to see how those were done, okay? All right, so let's go ahead and for me to solve this, I'm going to do the same thing that I did before. I'm going to change it to an exponential form. So the base of the log was a 9, so that's the base of my exponent, which is 9. The output of the log is the input of the exponential, which is 1/2. The input of the log becomes the output of my exponential, which is x over x minus 8. So when I do this, the 9 to the 1/2 is the square root of 9, which I know that's plus or minus 3. Okay, now I'm going to solve for x, multiply both sides by x minus 8, and solve for when 3 was positive and when 3 was negative, and I see that I have two solutions. I have x equals 12, x equals 6. And again, I want to check these values to see that I will get results. So when I check 12, um, it's a positive, so it gives me a solution. And when I check 6, one of the logs ends up to give me a negative, so 6 there is not a solution. 6 minus 8 gives me that negative 2, so hence 6 would not be a solution. So I only have one solution. Even though I got two answers, only one of them is correct. X equals 12. Okay. Oh, and that got me to the end um, with 7 minutes to spare. Well, thank you guys. Ms. Chuka, would you like to add anything to our students?
No, just want to wish everybody a great final, and we will see you all, I guess, next year. If you need to review when you take your next math class, and if there's some things you want to review, you can always join us. We'll be here at 11 as well. And thank you all for coming, and thank you everybody for helping us out.
Yes, thank you, Mr. Carizales. Thank you, Ms. Chuka. We do want to remind you all about the previously recorded sessions, which are available on the YouTube playlist. I shared that link a little bit earlier. This session will also be available on that playlist later today. Also linked is a short survey to help us improve our TVE sessions. Please take a few minutes to fill out that survey and remember to send your student ID number to us before you log out. If you would like to download a copy of the presentation, you can go to the top right corner and click on the box with the arrow going down while the presentation is on the screen. That'll allow you to download the presentation. Again, thank you all for coming in today. We hope you all have a lovely weekend and good luck on finals. If you have any questions, feel free to use the chat box or your mic, and online tutoring will also be available in case anyone would like to see a tutor. We hope everyone has a nice winter break. Good luck on finals and see you all next semester.